Hi, I'm Amer. I'm from Google. And so I'm going to be talking about JAX Privacy, which is our library for training differentially private machine learning models at Google. And I'm going to give some experience that we had with using this library from tuning large language models, mostly in practice. So this is joint work with a lot of people. Some of them are listed over here. And there's a lot of other people that also contributed to both JAX Privacy and some of the things we're going to be talking about. So just as a recap, LLM training has broadly two main parts. The first part is pre-training, and this is we train a base model on very large amounts of data. So there's something like trillions of tokens. This data comes from the web, mostly public data, but it might still contain lots of sensitive information. And then the second part of tuning is called fine tuning, and usually this is some proprietary datasets that are more targeted towards the actual kind of things you want your LLM to do. So there might be instruction following, or it might be code data, medical data, emails if you want your LLM to produce better emails, just whatever you want. This is going to be much more targeted, and usually the data here is very, very sensitive. It would be owned by some organization or some private individuals, and you wouldn't want to leak some of this data into for the models. And so the next thing I'm going to talk about is what kind of attacks am I really specifically talking about when I say we're talking about protecting users. So what I'm talking about is extraction attacks, and what they might look like is something like this. So let's say Harry Potter is a very common book, and it's most likely included in your pre-training data. And so you might prompt the LLM something like, hey, my name is Harry Potter. Can you remind me who my parents are? And the LLM will output James and Lily Potter. And this is because the LLM was trained on this data, and it has information about who Harry Potter's parents are. And now you can imagine there might be more sensitive data on the internet that has similar information, and the LLM would also answer those type of questions. And so we can look at scenario B here, which is maybe more private data. And so you might ask something like, hi, my name is Jane Doe. Can you give me the results of my recent health check? And now the LLM outputs, of course, Joe, you were diagnosed with this thing. And so that might be kind of bad. And so this is not just something that is we're imagining or pretending that this could happen, but there's definitely a lot of research work around this to see that this actually happens. So I've linked a paper on the bottom over here. This is a couple of years old. It was looking at ChatGPT 3.5, but specifically what they found is let's say if you prompted ChatGPT with just the word poem 50 times, then it would just start outputting its training data maybe 10% of the time, which is still pretty bad. So now I want to kind of present one of the ways we can tackle this kind of problem is using differential privacy. And what differential privacy means is I guess it's the privacy of a single unit, which is in this case would be an example. So adding this example doesn't change the output too much. That's kind of basically what it means. It is a nice formal mathematical definition, and also when we train with differential privacy, we get some kind of mathematical proof to go along with it. And that's kind of nice, but the downside is that it does cost more resources, and it does degrade utility. And I'm sure everyone knows this. I saw a few talks about differential privacy this morning already. So the next thing I'm going to talk about is the primary algorithm we use for training differentially private machine learning models. This is called DPSTD. There are a bunch of variations of this algorithm, but they all kind of go very similar to a regular ML training algorithm like STD. So basically, first we'd sample a batch of data. Usually, in regular training, this would be sampled with a fixed batch size, and also maybe the data set is only shuffled. In this case, we actually have to sample with Poisson sampling. There are other sampling mechanisms available, but this one usually we have the tightest accounting for this one, and also it's I guess, the best analyzed. Then next, like we calculate like the gradients using back propagation. In DPSTD, we do have to clip these gradients so that like each example's contribution is bounded. Then we sum these gradients and add some noise, and then we perform the model update. This is pretty straightforward from like just an SGD type of algorithm with just like 2 extra additions, which is like the clipping and the noising. There are like lots of like choices to be made here. Like these can be different things, like based on like like what kind of performance characteristics you want, as well as like the type of noise can change like like what kind of maybe utility you might get. So next, I want to introduce JAX Privacy. So JAX Privacy is like the primary library that we're using for like private training at Google. So this is an open source library. It's built on top of JAX. If you're not familiar with JAX, JAX is like a library similar to NumPy, but it runs on like accelerators like GPUs and TPUs, and it also supports AutoGrad. We think JAX Privacy is fairly optimized. It's fairly scalable, and we'll see like we were able to train pretty large models using this. We also try to like make the interface very, very nice and clean, and we did a lot of work on this. So what that means is like we think JAX Privacy is pretty versatile and extensible. So like we were able to implement many different types of DPSGD style algorithms in it. We do have like multiple APIs for it. Like so we have a JAX API, which is more targeted towards researchers, versus a Keras API that maybe is more for practitioners. And I think the last thing is kind of important is we try to like fix as many bugs as we find. I think there's a later talk on this, like that there's a lot of like great work on like differential privacy, but it's very easy to make mistakes, and like differential privacy in theory does not mean that you might have it in practice. So first, I'm going to talk about like our first case study, which is VaultGemma. So this is a 1 billion parameter model that we trained from scratch. So this is just like a regular causal LLM, and it was trained on 13 trillion tokens, and has an epsilon of 2. It's has a sequence length of about 1,000 tokens, so we can make predictions on that size. To get this to actually work, like we had to train for like really a large amount of time. So we had to use a very, very large batch size of around like 520,000 sequences in each batch, and then we trained it for 100,000 iterations. This is roughly like 4 times over the data set. And JAX Privacy was like very vital for us to like be able to do this for a few reasons. Like we actually have like a fairly like I would say performant gradient clipping algorithm in JAX Privacy, and we also support like tricks like gradient accumulation, or like the best accounting, or like just making sure like we support like all kind of data parallelism and model parallelism out of the box. And so that was like super useful for like getting this to work. One thing I kind of want to talk about is like like again coming back to the correctness bit from the slide earlier, is that like it's very easy to make mistakes while you're training like with DP, and I've made a lot of mistakes like over the 5-6 years I've been working in the space. And so we've tried to fix a lot of these bugs in JAX Privacy, and I hope like like if you do find a bug, then you can go ahead and like fix it in the open source version. So to give you an example, like while we were training VaultGemma, I spent like more than like 3 weeks just debugging where like the model would become unstable after training for a few iterations. And this was just because like we were using like floating point 16 data type for like the noise generation instead of float 32. And so this was super hard to debug, and it took me so long. But hopefully it doesn't happen again. The other example I kind of want to talk about is like like pre-training is like very resource intensive, and also like maybe not as sensitive as like the fine-tuning application. So like for the most part, like I would expect that like you would be using DP to fine-tune LLMs on like some kind of like very sensitive data sets. And that is also something that we support in JAX Privacy pretty well. Sorry. So in this case, like here's an example of like what a regular pipeline for like fine-tuning, let's say a Gemma 3 model would look like. You would load it like, this is using the Keras API. You would load the model, you would enable something called LoRa, which is just like a way to like do more parameter efficient tuning. You choose some kind of optimizer, you would compile it, and you would fit it on your training data set. To add DP to it, like at least from our API, it would be quite simple. We don't have to do too much. We only have to like make a new config saying like what the DP parameters are going to be. So in this case, like we chose epsilon to be 5 and delta to be 1 negative e to the 5. We choose some kind of clipping norm, batch size, training size, and then we can just call like this method called make private. And that's kind of all we have to do. Like we don't really have to change the rest of the training code. And this should just work out of the box to give you like some kind of DP fine-tuning on Gemma models. To give you some example, like of scale, like we were able to use this kind of like our JAX Privacy to train models up to like almost 30 billion parameters. So I would say like it is fairly scalable, and you can train like modern size LLMs with it. The next thing I want to talk about is like we've so far talked about like training with DP, and it comes with like a theoretical guarantee, and that's well and good. But we should also, at least at Google, we believe we should also look at like the empirical side of things and see like if we audit these models, like are we actually like respecting privacy as we expect? So to do this, we've kind of like, so these are like some experiments that an intern ran for us, and I'll kind of talk about like what they do and like what kind of like empirical privacy they measure. So the first one is like a credit card task, and like here like this is kind of somewhat of a generated example. Like it's not like realistic, but the point is like you're given like some kind of customer ID, and you're supposed to predict a 16-digit card number for it. These kinds of data is definitely not in like your pre-training set, and it's very, very specific. So it's very easy to see like if it was like, there was a leak. The other task we looked at is like a PII task where like, we give like someone's name and ask like what their job is. This kind of task maybe is like, the model could realistically guess sometimes to get the right answer, or this information could also be in the pre-training data in some ways. And so the first task we kind of use like to get like some kind of like upper bound of like what kind of memorization we see in our model. And the second task would be like some kind of more realistic prediction. And so we ran this like we ran some experiments like using these two tasks on our, I think this is on the Gemma 1 model as well, or sorry, Gemma 3 1 billion parameter model. And so we measure something called NP extractability, and this is basically saying like if you have some limited budget of like 2,000 attempts, like you should be able to get the right answer with like 90% probability. And so if the original data is like is only duplicated once, I guess I say 0 duplications here. What it means is just one copy. For the credit card task, like that's quite hard. The model is not really even able to do it even in the non-private setting. But once you get to like 8 duplications or 16 duplications, the model gets quite good at predicting these credit card numbers. With DPVC, these they go down, so like that kind of gives us some confidence that our differential privacy guarantee is actually working. Similarly, we see the same thing for like the job prediction task. The probability of getting things right goes up dramatically as like the number of duplications increase in our data set, but with DP, it doesn't seem to matter that much. Yeah. And finally, like I'd like to give some practical advice on training DP models. This is like based on my experience on like training VaultGemma, as well as like we had a paper on scaling laws for LLMs with DP, and we had some findings from there, and just want to share those. The first thing I would say is like if you're doing like any kind of like DPML training, especially using like DPSTD type of algorithms, batch size is super important. So like using very large batch sizes improves like your noise to signal ratio. And so you should definitely use the largest one that you can pretty much. And JAX Privacy helps you do this by like, having gradient accumulation and like having efficient clipping. The other thing I want to talk about is like learning rates. Like usually like choosing a smaller learning rate than non-DP training is useful just because like the additional noise during training causes slightly more instability. The other things I want to mention is like you want to choose like smaller models or ideally like some kind of parameter efficient tuning methods like LoRa. This reduces like the number of trainable parameters that you need to like update with your DP guarantee, and that dramatically helps with like utility as well. The last thing I want to say is like training with DP can have like additional memory challenges, and so like you can use that like like there's a lot of techniques in JAX Privacy like micro batching or gradient accumulation that can help you with that. So that's kind of all I have. And so here's a link, like GitHub link to JAX Privacy. Yeah, that's pretty much it. Like, if you like this work, please use it. You're welcome to make like contributions to it. Like there have been multiple people outside of Google that have made like algorithmic and like non-algorithmic contributions to JAX Privacy. And yeah, that's kind of it.